Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
Deep inside a glass fiber plant, ordinary minerals are pushed to their limit. This is the material born from fire. Silica sand, limestone, and alumina enter a furnace where temperature rises beyond imagination. Solid particles slowly disappear. Chemical reactions begin. Bubbles escape. The material becomes a glowing liquid, molten glass. But it is not for bottles or windows. Instead, it is forced through thousands of microscopic holes, pulled at high speed and cooled in milliseconds. A material that starts as sand becomes a high-strength engineering fiber. Today, we decode the complete engineering behind this process. To understand glass fiber, we must first understand the problem it solves, making structures strong, lightweight, and durable. When glass fiber is combined with resin, it creates GFRP, a composite where the fiber carries much of the tensile load. The relationship is similar to reinforced concrete. Resin holds the form, while glass fibers provide the tensile strength. This relationship is the enabling technology behind wind turbine blades, marine boats, and acid-resistant chemical pipelines. In electronics, these fibers provide the critical insulation and dimensional stability needed for modern circuit boards. Without it, many lightweight and corrosion-resistant structures would simply be impossible or far too costly to build. Glass itself is ancient. For thousands of years, humans have known how to stretch hot glass into decorative threads. But industrial glass fiber was a 20th century achievement, born when researchers experimented with high-pressure air jets. Initially used for insulation, engineers soon realized that continuous filaments could become structural reinforcements for aerospace. The modern idea is deeper, controlling chemistry, viscosity, and strand architecture at a massive industrial scale. The main building block is silica, silicon dioxide. It forms the backbone of the glass network. Pure silica is difficult to process because of its high melting temperature. We use carefully selected oxide mixtures instead. Common raw materials include limestone, dolomite, kaolin, and boron minerals. Each oxide has a specific purpose. Alumina improves strength and durability, while boron oxide helps reduce the melting temperature for better processability. E-glass is the global standard for general reinforcement, while S-glass offers the extreme strength needed for defense. C-glass provides better chemical resistance, while AR glass is designed specifically for reinforcing cement and concrete. If the recipe is wrong, the furnace struggles. In this plant, chemistry is the foundation of production stability. The first real operation is batching. Raw materials are weighed and mixed with extreme precision before entering the furnace. Materials are stored in silos and weighed according to strict formulations. Accuracy here is critical for the melt quality. After weighing, materials are mixed thoroughly. Sometimes recycled glass cullet is added to help speed up the melting process. Modern systems use enclosed conveyors and dust collectors to maintain safety and prevent environmental contamination. The furnace is the heart of the plant. It must maintain extreme temperatures for years of continuous operation. You cannot simply switch these furnaces off. Thermal cycling would damage the refractory lining, causing millions in losses. Inside, minerals soften, carbonates decompose, and bubbles escape. This is a total physical and chemical transformation. The lining must survive corrosive molten glass and extreme thermal stress for many years without failure. Modern furnaces use advanced combustion systems like oxy-fuel or electric boosting to maintain uniform quality. One word controls everything here: viscosity. It is the measure of the molten glass's resistance to flow. It must be hot enough to flow through the bushing, but viscous enough to stretch into fibers without breaking. After melting, the glass is refined to remove tiny bubbles. A single bubble can cause a filament to snap during extrusion. Conditioning brings the melt to the perfect temperature before it reaches the final, most precise stage of production. The melt must remain glassy and uniform. Unwanted crystal formation or devitrification must be strictly avoided. This is the bushing, a precision extrusion die made from platinum-rhodium alloy to survive the extreme heat. Platinum provides the corrosion resistance needed to handle molten silica. Each hole creates a single, continuous filament. Mechanical winding pulls the glass streams at high speed, thinning them from liquid blobs into microscopic fibers. Drawing speed controls the final diameter. These fibers are often thinner than a human hair, yet remarkably strong. At this microscopic scale, glass becomes flexible. By changing the geometry, we completely change the material behavior. As they leave the bushing, the fibers are cooled in milliseconds. This freezes the glass into its final solid state. Because they are so thin, heat leaves them instantly. It's heat transfer engineering at a microscopic scale. Next, the fibers receive sizing, a secret chemical coating that protects the surface from abrasion. Sizing protects the fiber, reduces static, and decides how well the material will bond with the final resin. Since glass strength depends on surface quality, sizing is critical to prevent microscopic scratches from reducing performance. Sizing acts as a bridge, allowing the inorganic glass to bond perfectly with the organic polymer resin in the final composite. Individual filaments are gathered into strands. These strands are the building blocks for every fiberglass product. Winding must be perfectly controlled. If the tension is too high, fibers may be damaged, too low, and the package fails. After winding, packages are dried to remove moisture and stabilize the sizing before being converted into roving or chopped strands. The final glass fiber can take many forms, from woven fabrics for aerospace to chopped strands for automotive molding. One of the biggest plant challenges is fiber breakage. A single unmelted grain or bubble can stop production. Breakage can be caused by bubbles, crystals, or even air turbulence. Operators monitor break rates with extreme care. Stability is everything. We monitor the process constantly to ensure the furnace and bushings are perfectly balanced. In the lab, we test for diameter, tensile strength, and resin wet out. Quality means the fiber performs correctly in the field. We measure linear density, often called TEX, to ensure the strand has the correct mass per unit length for the customer. Tensile testing measures the true limit of the material. We ensure every package meets the strict standards of modern engineering. Wet-out testing checks how easily resin penetrates the fiber. Poor wet-out creates voids and weakens the final composite. The true power of glass fiber is synergy. The resin provides the shape, while the fibers provide the load-bearing strength. Orientation is key. Aligned fibers provide strength in one direction, while woven fabrics offer multi-directional stability. In a properly engineered composite, the resin protects the fibers and transfers load between them for maximum performance. In wind blades, glass fiber allows for massive lengths that can handle extreme bending loads without failing. From boat hulls to chemical tanks, glass fiber makes lightweight, corrosion-resistant structures possible in harsh environments. Innovation continues. We are developing cleaner melting processes and AI systems that predict fiber breaks before they happen. The next frontier is sustainability, finding ways to recycle these massive composite structures at the end of their life. Fact: molten glass becomes solid fiber in milliseconds. It's a transformation of speed and precision born from fire. Glass is brittle as a bulk material, but as a fiber, its small size allows it to flex without breaking. Geometry is destiny. Troubleshooting is a constant discipline. Engineers must analyze the full chain from batch to winder to find the root cause. Troubleshooting begins at the source. Is the batch composition correct? Are there contaminants or unmelted grains? Safety is paramount. Handling molten glass and high-speed machinery requires extreme caution and rigorous PPE standards. We investigate the furnace. Even a small temperature fluctuation can change glass viscosity and trigger a cascade of breaks. Think of it like making noodles, but from fire through platinum and with the precision of aerospace engineering. Mechanical vibration or worn guides can create fuzz and surface damage. Every roller must be perfectly aligned. Let's recap. Minerals are melted, refined, and conditioned for the final transformation of liquid into structural fiber. Fibers are extruded, cooled, coated, and wound into the industrial packages that reinforce the infrastructure of our world. In the hot zone, safety is the first priority. Specialized PPE protects operators from intense thermal radiation. This is the story of molten silica. It teaches us that strength is about structure, surface, and precision design. From lockout-tagout to emergency response, the plant operates under a culture of rigorous safety control. From sand to superfiber, this is the engineering of glass fiber production. I'm Simple Guyan, and thanks for watching. Stay curious, keep engineering, see you in the next deep dive.